So it's my great pleasure today to have Professor Francis Hellman here from University of California in Berkeley. Francis has been a long list of accomplishments. She started as a PhD in applied physics at Stanford University, got her PhD in 1985, and then she was a postdoc at Bell Labs, assistant, associate, and professor at University of California, San Diego, and then chair of the Department of Physics at Berkeley at some point, and she has been president of the American Physical Society, dean of the Mathematical and Physics Sciences in University of California in Berkeley, and list goes on. She's working on understanding the physics of novel materials, magnetic materials, semiconducting and superconducting materials, and she's also doing some nanocalorimetry, which is how I got to know her. Yeah, list goes on, so I think I better just leave it for you, and welcome here.
Thank you. And thank you. And it's a great pleasure to be here, and I've so far greatly enjoyed my visit, including my first opportunity to be an opponent in a thesis defense, which was something I've never done before. So, and a great pleasure to get to meet, spend more time with Professor Reed. So I'm going to be telling you today about work I've been doing for quite a few years now on amorphous materials, and the talk is going to kind of divide itself into a couple of pieces. I'm going to give you an introduction to amorphous materials, because most people know very little about them. And then I'm going to give some examples of work we've done, particularly in magnetic materials and topological materials. And then I'm going to, from there, diverge out into talking about particularly amorphous silicon, where we've sort of uncovered some interesting properties that may have importance to gravitational wave detectors. And I'll tell you, along the way, I will explain what I mean by hidden order. And perhaps the most interesting part of all this is the idea that there is a disordered material that can have no entropy. And that's a thought that alarms many people. And I'll tell you why I think it's true. So this is work I've been doing for a long time, so I have a long list of collaborators, a whole lot of students up at the top, various other collaborators, both across the United States and also a couple here in the audience. Turns out you're having a conference, which ironically I was invited to give a talk at, and I declined because I had a conflict because I was on a thesis defense, which of course I didn't realize was the same location. So at any rate, it was sort of a funny moment when I realized that. Anyway, so I'm going to start, as I said, by giving you an introduction. And so let me make the starting point, which is almost, pretty much every textbook on condensed matter physics starts with a crystalline structure. And that crystalline structure then, from that basic, so I've shown just an example here, from that basic structure we have very well developed theories to explain why there are metals and why there are semiconductors and insulators, and we talk about band structure, we talk about a block wave description for the electrons, and we use Fermi gas, Fermi liquid theory, et cetera, et cetera. Of course, many in this audience, particularly with the conference, are trying to go beyond Fermi liquid kinds of theories, and I will touch on that later also. But this is just the basics. When I turn instead to an amorphous material, and I've shown here, that's a blobby mess that's actually taken from an old paper of Bernal's from, 100 years ago or so. Once I have an amorphous material, there is no long-range structural order, which in turn means that K is not a good quantum number anymore. So that means there is no band structure in the pure sense of the word. There is no block wave description of wave functions, but ironically, and well, I shouldn't even say ironically, but it is true that most of the properties that we are trying to describe in condensed matter physics still exist. So we have very good metals, we have very good insulators, we have semiconductors, we have superconductors. I assume everybody in this room is aware that there are amorphous superconductors. If you're not, you should be, because it's a remarkable I would claim, an even more emergent property that it occurs in in an amorphous material than a non-amorphous material, ferrimagnets, etc. So, and one of the points I want to make is that atomic energy levels overlap, which means that energy is still a perfectly good quantum number. And whether I'm talking about electrons or phonons, and there are phonons, and there are well-defined electrons in these materials. So I can still talk about energy bands, which means I can definitely still talk about an electron density of states. The Fermi energy is still a perfectly good concept. And kind of a bottom line, the properties depend on the preparation, and there are many amorphous materials used in many applications, not least of which, of course, is window glass, which is notably transparent. So just stop and think about that for a second. How, this was a great discovery to explain why window glass is transparent. And we'll come back to that point. But the structure is very hard to characterize. And so in general, people constantly ask me, well, how do you characterize the structure? And there are characterizations, I will touch on them, but I would claim and I would suggest to you all that structure is kind of the wrong way of looking at this, at the properties. You have big, broad distributions of function, structures, but if I asked you about the gas in this room and the ideal gas, I'm literally talking about an ideal gas. I'm going to come back to the ideal glass later. This is just an ideal gas. Nobody would think to ask the question of where are all the atoms? It's not, they exist. This is not some quantum problem. But it doesn't matter where all the atoms are. That's not the important point. You can talk about the pressure, you can talk about the volume, you can talk about temperature, heat capacity, entropy, enthalpy. You can use scalar quantities quite nicely. You can talk about average properties, but you're not going to ask, you just don't care. And I'm going to claim that's kind of true in amorphous materials also. So getting too focused on the structure doesn't get at the heart of the problem. And so the last point I want to make here is on amorphous superconductors. And so amorphous superconductors have been known for quite a while. The remarkable part is, how do I describe them? So I assume that everybody in the room has at least been exposed to BCS theory of superconductivity. BCS theory is couched in K-space, plus minus K-state pairing. Well, so what do I do when there is no K-space? K is not a good quantum number. It's not conserved. The electron scatter is, the mean free path in an amorphous metal is 1 angstrom. It's the interatomic distance. So scattering occurs constantly. So what am I going to do with BCS theory? All right, so the first statement is, we treat this, and most theorists think of it this way, it's an emergent phenomena, which means it doesn't care about the underlying structure. It just doesn't matter. I have a pure wave function that emerges. And so mostly, I have to be careful not to insult theorists too deeply, because there are theorists who are my best friends. So I will try not to be too insulting of them along the way. But the phrase that is most commonly used is that the phenomena is robust to disorder. So that's what most people would say about amorphous superconductivity. Okay, that's fine. But let's take an example. Let's consider amorphous and crystalline molybdenum. Crystalline molybdenum is a superconductor with a TC that is below a Kelvin. Amorphous molybdenum is a superconductor with a TC of 9 Kelvin. Well, maybe this is just me as an experimentalist speaking, but that does not sound like robust to disorder. The disorder has enhanced the TC by at least an order of magnitude. So it's kind of missing the point, at the very least, to say it's robust to disorder. You could equally well say the disorder caused the superconductivity. If I happen to be sitting at like 4 Kelvin, the crystalline one is not superconducting, and then I could disorder it, make it amorphous, and it would become a superconductor. So at the very least, I would say it's an even more dramatic example of an emergent phenomena, that in the normal state, the scattering is 1 angstrom, and then it goes superconducting, and it will, lifetime of the universe, carry a current with no energy loss. So that's a sort of, I would say, robust to disorder just does not do justice to what that is, to what you need to do. And what do you do with BCS theory? Well, there was a realization of what to do with BCS theory, and it was really Anderson. You don't talk about K-states anymore. You talk about time-reversed states. So if one electron comes through and scatters every angstrom, which it does. That is the mean free path. So scatter, 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 scatter. As long as there is no inelastic scattering event, which is not hard to, at low temperatures, there's very little inelastic scattering, then a backwards traveling electron will go back through exactly the same path. So we talk about time reverse states and their pairing. So at least I have a framework. I'd say the other thing that's interesting about this is when I make the Cooper pair that small, which I do because there's so much scattering, the Cooper pair is now very, very small. That's actually pretty good for superconductivity in a lot of ways. It makes it more type 2. It tends to enhance the upper critical field. So it's actually kind of a good thing to make it disordered in this way. All right, so that's just a philosophical point. Another practical point, amorphous materials are often very flat and very smooth. Crystalline materials, I'm going to be doing a lot, I'm an experimentalist, all my materials are going to be made by vapor deposition processes. So amorphous materials are useful for a whole lot of applications, in part because this is just an image of a multilayer. It happens to be a particular multilayer. It's a material, gadolinium, terbium, cobalt is a ternary alloy that is useful to magnetic recording properties, et cetera, et cetera. It's extremely tunable. You'll notice all the X's and Y's in here. I can change the composition quite continuously in these amorphous materials, in these alloys, in these sort of pseudo-binary alloys, and change all the properties in a totally tunable way. I can control the exchange parameter, I can control magnetic anisotropy, lots of things that I get to control in order to tune their properties. And this flatness is useful for a lot of things. So it happens to be particularly useful for LIGO, in the LIGO mirror coatings, which I will come back to at the end. But this is just an example. So the next few slides are gonna be all on amorphous magnetism and topological kinds of materials. This is a broad-based talk, so I'm going to touch on a lot of different areas and, with limited depth in each one. So what this is very old work. This is actually from back when I was a postdoc. So these images are actually direct screenshots of a paper because nothing was electronic, anyway. So this particular alloy, amorphous rare earth transition metal alloys, are really good ferrimagnets. The rare earth points one direction, the exchange coupling causes the transition metal to point the other way. So there's things like a compensation point, which I don't really want to call an anti-ferromagnet, but it's like it has M equals 0, let's just say. It's an M equals 0 ferrimagnet. Compensation, all sorts of things. The interesting thing is, when grown by vapor deposition processes, it has a perpendicular magnetic anisotropy, meaning it magnetizes out of the plane of the film, which, dipole coupling, normal magnetism, wants to lie in the plane of the film. Just adding up the magnetic dipoles, it will lie in the plane. So to make it want to point out of the plane, there has to be a structural anisotropy in there. It is, however, this is where I get back to my point about structure, it's very hard to see. So I have been involved in studies looking for the structural anisotropy, and with a kind eye on the data, you can see it. There's a slight shift in the partial distribution functions, but these are big, broad partial distribution functions of pairs, and there's a small shift of out of plane versus in plane. We've done simulations of growth, and it is, in the bottom line, it really is a growth-induced effect. So this amorphous structure remembers that it was grown like not an atom at a time, but in the end, sort of a plane at a time. So that out of plane is different than in plane because it traps a memory of that growth. And I will come back to where that comes from, but it turns out that is an extremely important property for magnetic recording. So having things that want to magnetize out of the plane is useful for all kinds of things, among other things, the Kerr effect, where you can bounce light off and it'll polarize and so forth. It also turns out that you can make a skyrmion out of this. So once you have a perpendicular anisotropy, it's not that hard to get something where it wants to make a curling of the magnetization. And it's quite easy to get that kind of a structure. So modern magnetism, lots of people are speculating on using skyrmions as the magnetic recording bits. They're topologically protected, which, of course, naively begs the question of, if you can't destroy them, how did you create them? So I'll leave you just musing over that little detail. But trust me, you can both create and destroy them. So the topological protection can get overstated. And this is just an image that I took from back then of various, we were studying correlation lengths in it, and was this a spin glass? You know, this was the era of sort of random anisotropy, random fields, things like that. So it turned out, nope, this is just a really good, pretty good, it acts like a ferrimagnet. Anyway, I could tell you more about correlation lengths, but not the topic today. So the point I want to raise is this growth-induced anisotropy effect, because this is going to be relevant, particularly when I get back to amorphous silicon. This is a plot now of the perpendicular anisotropy. Now, the nice thing about PMA is it is easy to measure. Unlike this tiny, tiny structural anisotropy, which you work incredibly hard to get a small displacement of partial distribution functions, magnetic anisotropy, it magnetizes out of the plane. I mean, you look at it with any kind of magnetic microscopy, and you see it's out of the plane. So the interesting thing about that is this is a plot of the magnitude, how much does it want to be out of the plane, as a function of the temperature at which I grew the film. So if I grew the film at room temperature, perpendicular. If I grow it at higher temperatures, more perpendicular, wants even more to be out of the plane. If I grow it at lower temperatures, it goes away. So this is not only growth-induced, it's not just a memory, it is a memory that is enhanced by growth temperature. It also goes away when I anneal. So there is an asymmetry between growth and annealing. So I can grow it, for example, here at like 400 Kelvin. If I grow it at 400 Kelvin, it is completely different than taking that room temperature and annealing at 400. If I grow it at 300 and then anneal it at 400, it's isotropic. It relaxes and it goes to an isotropic state. So this really is a growth-induced effect. So how should you think about that? Atoms are landing on the surface. They have a very high mobility in the plane and very little mobility perpendicular to the plane. So I'm creating something which at one point Marion Carter actually did a whole thing about layer by layer growth. And there's a way in which you're creating a particular kind of structure in this film by giving it, and that is common. In vapor deposition growth, it is common to find mobility, meaning an atom may be able to move thousands of angstroms before it gets buried by the next layer. So there may be the mobility perpendicular to the plane, may be 1 angstrom once it is buried, but prior to being buried, it can move a long way. So I can equilibrate the surface without it equilibrating the bulk. And that is going to be the heart of what I'm going to talk about. Okay, so I'm now going to flash through a few examples of things we've done. And so this is a particular, we had a whole thing looking at manganese-doped silicon and manganese-doped germanium. And those of you who don't have the periodic table just stuck in your head, which I pretty much do, but silicon and germanium are both, column 4, they're both semiconductors, they're both glass formers. So you can put almost anything with silicon and germanium, and it's likely to be amorphous. It's also likely to be homogeneous just because of the nature of the bonding. So this is a typical, we have to always check that we have made an amorphous material, so I'm only going to show this one example. That is a 14% manganese silicon. That is a high-resolution transmission electron microscopy. That's not going to mean much to any theorist in this room, but it should mean something to the experimentalists at least. That's what an amorphous material looks like. It doesn't look like anything. It just looks like that's a bunch of random looking patterns. Okay, so that's kind of typical, and that's a typical kind of diffraction pattern, quite expanded. All right, so the interesting thing about this particular study, and I'll tell you why I'm telling you about it in a second, we looked at manganese germanium and manganese silicon. This is a plot of the effective moment, like in its above its ordering temperature, and you can just, without sweating the details, completely different behavior. So even though germanium and silicon are both column 4, they're both like to have that kind of bonding, when you put manganese in them, they behave completely differently. And that carries over into everything. So one of them manganese ends up looking magnetic in the germanium. It's strongly anti-ferromagnetic interactions, so it's actually a spin glass. If you look at quantities like the density as a function, the atomic density as a function of composition, it looks as though you had manganese going in a substitutional kind of site. If I do look at silicon, I find the opposite. It's non-magnetic. It has, by the way, a negative Hall coefficient compared to a positive Hall coefficient. And it looks like it's an interstitial environment. So if I now go and look at crystalline silicon and ask the question of what happens when I put manganese into crystalline silicon or crystalline germanium, I find similar properties. It matters whether it's an interstitial or a substitutional environment. So about now, I hope you're thinking, how in the world do you tell the difference between a substitutional and an interstitial environment? That would be an excellent question. If we tried, so what we can do, we don't have some of the tools that you can do in perfect crystals, but you can look at how many neighbors things have. And so it turns out that in the germanium, you have, it's substitutional-like, so it tends to have 4 neighbors, and in the interstitial one, it tends to have 8 neighbors. So you can look at the average number of neighbors and see a difference. But isn't it more dramatic to look at the Hall effect? That's actually switch sign. There's nothing ambiguous about that Hall effect. The Hall effect of one is negative and the other one's positive. So whatever one thinks about whether something is, whether it's, you want to think substitutional versus interstitial, you have to deal with the fact that this has a positive versus a negative Hall effect. So my point here is amorphous may look to most people like a big blobby mess, but it isn't a big blobby mess. There are really distinct things you can say. There's other things you can't, but there are many things that are quite definitive. When I get to amorphous silicon, one of the things we talk about a lot is the number of dangling bonds in amorphous silicon, and that we measure with electron spin resonance, and you can count them. Despite the fact that I'm pretty sure you couldn't find them. If you could see all the atoms, you'd have trouble finding those missing bonds. It would just look like a bunch of silicon atoms. In fact, I'll show you an image of that. So my point is, it may look like a blobby mess, but it isn't. All right, so we also looked at iron silicon and iron germanium, and then now I want to make, the same point still applies, but I want to make yet a further point. So starting at the top here, what we found when we looked at iron germanium, and I think this is actually iron silicon here, so sorry about that little bit of mislabeling. But at any rate, the point is, as the magnetic moment per iron, as a function of the composition of this material, amorphous has more magnetization than the crystalline at all compositions. Significantly more. It's not just a small one. This is a theoretical data point of a totally disordered crystalline structure, but that's a theory that you can't make it like that. So that's the first thing. So what we actually find is we have enhanced magnetization, we have enhanced spin polarization at the Fermi energy, which we measured using a Andreev reflection experiment. We have an anomalous Hall effect, which the first sign we had was that it looked like it was intrinsic. And the reason I say it looked like it was intrinsic is because it didn't change, it didn't scale with the resistivity the way you would expect a scattering induced anomalous Hall effect to depend. So we had indications that it was an intrinsic anomalous Hall effect. Now at this point, anybody who is in condensed matter should already be getting a little alarmed, because the intrinsic anomalous Hall effect is attributed to a Berry phase curvature. Okay, and so any condensed matter theorist, that's the way you calculate the intrinsic anomalous Hall effect. You take the crystal structure and you calculate the Berry phase curvature. Those of you who have no idea what a Berry phase curvature is, don't worry about it. It is a pretty hardcore condensed matter concept. It is a derivative in K-space. All right, so derivative in K-space, I don't even have K-space. So how in the world do I have a derivative in K-space if I don't even have K-space? So the answer we worked out after a while was everybody's happy with doing a density of electron states. I don't think anybody has qualms around that idea, that I can have that energy is still a good quantum number, therefore the density of states is fine. I can talk about energy space. You can do an analogous effect called the density of curvature, which is a Berry curvature-like calculation. You do it the way you do all amorphous materials density functional theory, you make an enormous unit cell inside of which it's melted and then quenched, sort of like you would do in real life. Melted, quenched, you do it a bunch of different times so that you have a whole bunch of manifestations and you average over all of those. This is a plot of the density of curvature. Out of that integral, just like you would do in a crystalline structure, you take the integral and you get the anomalous Hall effect. So I don't know if I've convinced you or not, the paper's there if you want to go look at it, but I hope I've convinced you that we can talk about a Berry curvature, a density of Berry curvature in an amorphous material and calculate the anomalous Hall effect. Okay? So that was sort of one of our first results in these amorphous materials. Okay, next one I want to turn to. So that one usually flies. I've not had people really struggle with that one as much as this next one. So the next one I'm going to talk about is an amorphous topological insulator. All right, so there, I believe, are still theorists in this world who do not believe that that is possible because topological insulators seem like a very band structure derived effect. But I hope I can convince you that that is not true. There are, in fact, amorphous topological insulators. So this work actually started because there was a FISREV letter that I saw, and it is a calculation in a specific. It's a type binding model. They include spin-orbit coupling, and they showed that there was a topological phase, quantized conductance, and localized edge states. So I saw that, and I thought, that's cool. Maybe I can grow this. So that was where this project started. Then the pandemic happened. So we all went home. You all presumably went home too. But as experimentalists, there wasn't very much we could do in our homes. So the student I had working, we decided to see if we could calculate something. And so he came up with the idea of taking bismuth tellurium iodine, which in the crystalline form is, I hesitate to use the word trivial insulator, but that is what is common. It is called a trivial insulator. To be slightly more exact, it's a Rashba semiconductor. But it is not topological, is the point. It turns out it has a rather small gap, and it turns out that under pressure, the bands invert, and it becomes a topological insulator. So that means that the topological state is not very, the ground states are not that different in energy. So the theory my student had, and this is all him, this part, he thought, let's try putting this in a computer, and in a computer you start with a crystal structure, and he then introduced random XYZ displacements. Not the same as an amorphous material, but certainly mimicking one. And what he found is as he did random XYZ displacements, there was a critical value of average displacement at which the bands inverted. So we had as a function of the amount of disorder in this material, we could induce a trivial insulator to a topological insulator transition. All right, so that already to me feels like it proves the point that I have it's not an amorphous material, it still has sort of an underlying crystal-like, states, but it seemed like a good way forward. Okay, so that was the next thing, and that's the relevant papers, and that's actually where we started working with people like Adolfo and then Peru and so forth on some of these ideas. Okay, so that was the theory paper. So the next thing we were doing kind of in parallel at this point is we decided to try and grow amorphous bismuth selenide. So bismuth selenide is a well-known crystalline topological insulator, and it turns out if you grow it kind of at room temperature, it's actually fairly easy to do. And you have to be careful. I want to really distinguish nanocrystalline from amorphous. Okay, so I'm going to come back to nanocrystalline. It has to be amorphous. But if you grow amorphous bismuth selenide, you get a topological insulator. Now, to be really exact, and I need to be really exact here because the referee would not accept the paper until we change the title. So if you look up this paper, you will see it is not called amorphous topological insulator. It is called Evidence for Spin Momentum Locked Surface States in an Amorphous Material. Okay, so that was the compromise. We were not going to get this paper published without that change. If anybody who knows about topological insulators, the words spin momentum locked surface states, it's hard not to think topological insulator. But beauty's in the eye of the beholder, so you get to call it whatever you want. The alternative that we couldn't disprove was that it could have been a Rashba effect, but it would have been it was like by a factor of 100, the largest Rashba splitting that anybody would have ever seen. And, again, maybe I'm just as an experimentalist speaking, but I had a lot of trouble understanding why the reviewer would think that finding something with 100 times larger Rashba splitting than anybody has ever seen, why that felt better to them than calling it amorphous topological insulator, I don't know. This is the downside of trying to publish in Nature, which was not my choice. So, at any rate, that is the evidence for it. That's the spin ARPAS, showing the spin momentum locking, blue being one spin and pink being the other. So there's some interesting things which I don't really want to get into, but there's some interesting things in the dispersion of this ARPAS. It has like this very vertical dispersion relation that apparently, again, I'm not really an ARPAS expert, but apparently is seen in some of the high TC and some other materials where it's attributed to disorder. So we now have another collaboration with an ARPAS person, and she's very excited by trying to figure out whether it's the same thing. It looks kind of the same. So maybe we'll learn something about high TC, I don't know. Okay, so that I am now going to move on and talk about amorphous silicon. And so amorphous silicon, I'm going to start by showing you, there's the crystal structure, it's diamond structure. I don't know if people know that, but it is the diamond structure. So each silicon is bonded to 4 atoms in the crystalline structure. There is a tetrahedral bond angle of 109.5, and of course in the crystal, every atom has that. There are, of course, defects. I mean, I feel like I have to remind people that there is actually no such thing as a perfect crystal. They always have defects. So, but at any rate, that is the idea. Now, here is an example of the amorphous structure, in a computer. And this looks like a jumbled mess, right? I mean, if you just sort of look at it, it looks like, oh my gosh, there's just atoms everywhere. But if you actually look at any individual atom, it is 4-fold coordinated. It has a bond angle that is very close to 109.5. So the global statement is amorphous materials have a huge amount of short-range order. They just don't have long-range order. They're also not nanocrystalline. Oh, and I meant to make that point on the previous slide about bismuth selenide, so I'll make it now. It's a little bit out of date. So amorphous bismuth selenide is spin momentum locked surface states. Crystalline is a topological insulator. Nanocrystalline bismuth selenide does not have any of those properties. So nanocrystalline, which sometimes is hard to distinguish. Many people, if you only do X-ray diffraction, you will not distinguish them. But nanocrystalline is not the same as amorphous, nor is it a continuous transition from one to the other. The amorphous state is a distinct one from a nanocrystalline state. Nanocrystalline state does not support the topological insulator, so none of the properties that characterize a topological insulator are seen in nanocrystalline bismuth selenide. That was actually the heart of the reviewer's problem. It turns out they were making films and not seeing these properties, so they just sort of didn't believe us. So we ended up making the nanocrystalline to show what they were seeing. Anyway, all right, so the point is, there's no long-range order, but it is very ordered locally. There is short range, there is medium range order. You can quantify those. These, as well as the atomic density, depend on how you prepare them, and in particular, with amorphous silicon, I'm going to show you some data, increase with annealing, increase with growth temperature. So the amorphous phase is actually quite controllable, even if you can't always characterize it. And so the question underlying all this is how to think about it thermodynamically. So I'm not going to go through this. I'm an experimentalist. I've been working on amorphous silicon now for easily 10 years, and we have done a lot of measurements. I'll only mention we grow the films. It's all by vapor deposition, high vacuum. We do measure the characteristic dangling bonds by electron spin resonance. We measure density. We measure, here's all the types of characterizations we do. So there's quite a wealth of characterization we have done. The only one I really want to show you is the high resolution and low resolution. So these are transmission electron microscopy images. I'm going to show you a whole lot of how this depends on growth temperature. You remember back with that terbium iron where the growth temperature caused the perpendicular anisotropy to increase? And I didn't actually point this out at the time, but should have. That turns over when it starts to crystallize. So as soon as the material starts to crystallize, it's a different thing. So we're going to find sort of the same thing here. So here is what this looks like, these two, when it is grown near room temperature. And here is what it looks like when it's grown at 400 C. And they look the same. So the real point there is you can look at that as much as you want and you will not find a difference there. Okay? So growth at 400 C, which you're going to shortly see, leads to a really different set of properties than growth at room temperature, is not visibly structurally different. Okay, so moving on, I told amorphous silicon, so I've mentioned already that there is this 109.5 degree characteristic angle. One of the things you can do with Raman is you can characterize that bond angle and you get a distribution. So the amorphous structure, it turns out the bond length is very, it really doesn't change. So the bond length in amorphous silicon is the same as crystalline silicon. The bond angle is also almost the same. It's 109.5 plus minus a full width, there's a full width half maximum to the distribution. So it turns out if you grow at room temperature, the full width half maximum is 10 degrees. So it's 109.5 plus or minus 5 degrees. So by eye, I doubt you could even see that. If I make really what I'm going to call good, and I'll come back to what I mean by good, but just allow me to call it good for right now. If I grow it at 400 C, the bond angle distribution drops to 8 degrees. So really good amorphous silicon has plus minus 4 degrees. Again, you would be hard pressed to see it. You can do other things like sound velocity. You can measure the sound velocity. There's the crystalline values, longitudinal and transverse. And what you find is when you grow it at room temperature, the sound velocity is a little bit lower. Then as I start growing at higher temperatures, the sound velocity gets really close to that of the crystal, both of them. So, okay, there. A little bit of structure. If I look at the atomic density, I start seeing some interesting and what turns out to be very important things. So this is the atomic density. Sorry, I've changed scales. I'm now in Kelvin here. So so it depends strongly on the growth temperature. There's the crystalline silicon density. So if I grow at sort of 700 Kelvin, I get really close to crystalline density. If I grow at lower temperatures, I exponentially as a function of thickness. So what I'm telling you is that the atomic density depends on growth temperature, thickness, and rate, by the way. So that's interesting, a little weird. These densities are actually modestly low. You're not going to get to those kind of low densities by, thinking about small bond angle deviations. In fact, the breakthrough on understanding this was when we did positron annihilation studies. It turns out there's nanovoids in here. That is a common thing to have happen in silicon specifically, but in many amorphous materials. You form these tiny little voids, few atoms in size, that take account of the strain. They help minimize the strain, the internal strain. So these little tiny voids are impossible to see in transmission electron microscopy because there's nothing there. So you don't see anything. There's not a visible hole. But they turn out to explain this density and turn out to be important to the thing I'm going to show you in a second. All right, so with that background on amorphous silicon, I'm going to briefly tell you about the property of tunneling level states. Some of you, and probably not very many of you, know already about tunneling level states. So there is a whole set of properties known as the universal glass properties, which are all low temperature properties. And so those low temperature properties, I'm going to here focus on the heat capacity. This was work done by Bobby Pohl, or summarized in a very famous paper by him. There is an excess heat capacity at low temperatures in glassy materials. Now, heat capacity, as we've, my host we've been discussing quite a bit. Heat capacity is hard to do on small samples. It's mostly done on bulk samples. So most studies of the glassy state, of the amorphous state, have been done on liquid quenched glasses. meaning just what it sounds like. You take the liquid, you splat it down on a cold surface, and you hopefully have a glassy material. Some things like silica, SiO2, you can actually cool pretty slowly. That's why we can, blow beautiful Chihuly pieces of glass out of it, because you can cool it quite slowly and it will not crystallize. It will stay in that glassy state. Other things you have to quench very quickly. Silicon is really silicon, not silica. Silicon is an anomaly because the liquid state is 5-fold coordinated. You cannot quench that. If you try to quench that, the extra energy in there just literally it blows up. And I'm not kidding. I've had it blow up in my growth chambers. If you quench the liquid of silicon and you get little regions that are trying to be 5-fold coordinated, it has so much extra energy that it explodes. And you have flying molten silicon all over your growth chamber, melting holes in like viewports and things like that. So not good. So you can't quench liquid silicon. So interestingly, it's very easy to make it amorphous by vapor deposition processes. Okay, so getting back to these, so this is the classic experiment on silica, where this is the heat capacity divided by T cubed. Here's what the crystal looks like. There's the Debye temperature where it looks flat. That's just the T cubed law of a crystal. And so you can measure the sound velocity, you can derive what the heat capacity, and it really matches. There's the heat capacity lining right up with what you calculate from the sound velocity and the density and so forth. Then you do the same thing with what's here called vitreous, which is liquid quenched, and you find several things. One is this so-called boson peak, which moves a bit, not very much. People talk about them in totally different languages. This is not a talk on the boson peak, but I'd be happy if somebody wants to ask about it. It's hard not to see those as the same thing. So at any rate, the people have a lot of opinions on that. The biggest thing you would find is that this, what you can measure the sound velocity, which, by the way, if anybody was curious about that, well-defined sound velocity. You can absolutely propagate phonons, and you can launch them and propagate them, and, absorb them and so forth. So it's down here. It's a little bit softer. So amorphous silica is a little bit softer, a little bit lower Debye temperature, but not by very much. But this is too high. So the first thing is this is not coming in at the Debye temperature. Second thing is there's this enormous upturn, which an upturn on C over T cubed is a linear term. Or it could be other things, but it is a linear term. And that huge linear term was a great mystery. These are insulators. There are no electrons in here. I mean, there are no free electrons in here. So this was known for quite a while and was explained by what's called the standard tunneling model. So it turns out that, which I'll show you in a second, I'm going to show you one other property, which is the internal friction. The internal friction, think Q. So if I take a crystal of anything and I set it ringing, I make it vibrate, a crystal will vibrate sometimes for days. When you take an amorphous material, it damps out much quicker. So there is a damping mechanism. There is a way in which these coherent phonons of the ringing the energy gets dissipated. So mechanical loss is a measure of that dissipation. So what you find is that this is one of the most prominent so-called universal glass properties, is that at low temperatures, this internal friction has this plateau. Crystalline materials don't do that. They have all kinds of peaks and stuff like that, but crystalline materials typically are, this is 1 over Q, by the way, so low on this scale is high Q. So crystalline materials are way down here. Some of them even, you can make beautiful single crystals that'll ring for days if you really work at it. But the glasses, this is the so-called universal range. So the standard tunneling model, which I'll show you in a second, explains that there is a plateau, because that's not easy to explain. But you can explain that plateau, and you can also explain the heat capacity linear term in this tunneling model, but you don't get the universal range. So explaining why there is a universal number, an actual number for materials as different as all of the things that are shown in this plot, has been a long-standing mystery, and I'd say is still actually not resolved. Why there is some universal number. Okay, so standard tunneling model, we're going to do this quickly. We're not going to try and do all the math, quite obviously. But this was derived, this is supposed to be that big blobby mess of atoms that I showed you at the beginning, which obviously has very little to do with any real material, but it's a good model. So I'm going to imagine that I have something like this, and I've color-coded a few atoms, because what I'm going to point out is that this arrangement can transform to this arrangement by moving the red atom a little bit to the right, and then the yellow atoms move a little bit also, and the green atoms not very much. That clearly can happen through a thermally activated process, like, so the atoms, if I'm just to use my hands, the atoms in an amorphous material are not trapped in a single location. You can imagine that they can distort just a little bit to another state. So if they can get there by thermal activation at low temperature, they can get there by tunneling. And that is the heart of this model. So they tunnel they thermally activate high temperature, they tunnel at lower temperature, and then out of that I construct this model quantitatively. I have a double potential well, and I can tunnel between these two states, so I get a quantum mechanical, plus minus of the states, and that gives me a splitting in energy that depends on the height of the barrier. So a typical height of the barrier is like 1 electron volt. That's a normal sort of potential barrier in a material. But that means I can get splittings that are micro electron volts. And I have a whole range of them because this is disordered. And since I have a whole range of them, I can have a whole range of states that are split only by micro electron volts or even less. So you can immediately see, I hope, where the heat capacity, a linear heat capacity comes out of that. And so does the plateau in the internal friction. Okay, so the standard tunneling model explains the low temperature loss and things like that. It does not explain why there is a universal number. So now I'm going to jump to what I've seen in amorphous silicon and why I talked about good and bad. So here is a plot of the internal friction. Remember, everything was up in this. The universal range is shown here by this little, that's the range, 10 to the minus 3 to 10 to the minus 4. Here is silica, which lies nicely in the middle of that universal range. Here is silicon when I grow it at room temperature, also kind of nicely in the universal range. There's no universal range at room temperature, although things don't deviate that much, but that's not where anybody talks about universal range. So there's room temperature amorphous silicon. Look what happens as I start raising my growth temperature. And remember, I showed you already, this is still amorphous. In fact, structurally, they really look, the bond angle deviation goes down a little bit, but not very much. Look what happens when I grow it at 400 centigrade. I'm down to where I really almost can't, it's indistinguishable from a crystal. Crystals can go lower, but this is down at 10 to the minus 6. So I am wildly out of the universal range now. I am now couple of orders of magnitude reduced by growing amorphous silicon at this elevated temperature, which is definitely not crystallized. Okay, so it also shows up in the heat capacity the same way. I have a huge linear term when films are grown at room temperature, goes away as I go to higher temperature. Okay, it also there's other characteristic properties, but that's the important point. So where does this come from, and why am I telling you about it so much? I now want to, hopefully people have seen an energy landscape before. If you haven't, I'll try and walk you through a bit. So let's just start with the thing on the right. So what I'm plotting on the right is the energy of a material. Let's start with the easy one, the crystal. So I take a crystal of some material and I calculate its internal energy, or I measure its internal energy. And that gives me a point on this plot. And I choose to put this x-axis is really quite arbitrary, but I'm going to pick a place that I'm going to put the crystal, and there is its dot. That's its internal energy. Now I'm going to do the same thing for an amorphous material. I liquid quench it a whole bunch of times. I do this in a computer. I do something. This actually is a calculation. What I'm showing you here is like a Leonard-Jones potential. So you can calculate these things. But every time you do this, you're going to get a different energy. So you calculate all these energies for all the many different amorphous structures. And I now put things on this plot where I've somehow decided and somehow figured out I'm going to put things near each other that are near each other in configuration space. That is obviously a loose definition of what this z-axis is. But the end result is something that you hopefully have all seen, which is this complex energy landscape of an amorphous material. You see this for proteins, you see it for spin glasses, you see it in lots of systems. Very complex energy landscape. And I'll come back to why I'm labeling this the ideal glass. But the whole idea is that at high temperatures, I'm up here where I'm skating across, that's the liquid basically. At that point, I'm skating across all these structures. This is potential energy, right? I'm not doing free energy here. As I start lowering the temperature, you start getting trapped. So if I'm liquid quenching, this is straightforward. I lower the temperature and I will get trapped in one of these many wells, and I lower the temperature more and more and more, and so I will get trapped. Okay, I can map, now let me talk about the left-hand side, which is entropy. So I can also talk about the entropy of all these states, and of course we know the entropy of the crystal, we're not going to include vibrational, but the configurational entropy is 0. So here I am in the liquid state. In the liquid state, I absolutely get to talk about entropy. I can talk about entropy, volumes, heat capacity, all thermodynamics, quite happily. So up here in the liquid state, no problem. Plot entropy, there's one data point up there. Start cooling it down. I get to here, and if it crystallizes, if the material crystallizes, you'll then have a discontinuous jump in the entropy, right? That's the first order traditional phase transition. So I get a discontinuous drop, but I can bypass that if I can supercool. And so I'm going to supercool this liquid, and then, so this is an important point. The supercooled liquid, I still get to talk about entropy and enthalpy and volume and pressure and all those things. It does not have to be the ground state to enable me to do thermodynamics. You all know that because nobody has a qualm about talking about the entropy and enthalpy and things like that about diamond, and yet I assume you all know that diamond is not the ground state. So it does not have to be the ground state, it just has to be reversible. The supercooled liquid is a perfectly fine place to do thermodynamic measurements as long as it stays reversible. So I'm going to follow the entropy down like that, and at some point it is going to fall out of equilibrium. When it falls out of equilibrium, that is the glass transition, a huge field of study. But at that point, you have to be careful, because once it falls out of equilibrium, it's not reversible. You really do not get to keep following the entropy anymore. Let's just put it concretely. The integral of C over T doesn't mean that same thing anymore, because it's not reversible. You go through the glass transition, you fall out of equilibrium. So that happens at some point in here. But the interesting thing about this is there's a natural extrapolation. You may not ever get there experimentally, but there is a very natural extrapolation of this curve, shown in a little dashed line here, which reaches the entropy of the crystal. This was realized quite a long time ago, and it was called the Kautzmann paradox. It was studied by a man named Kautzmann. And this is called the Kautzmann temperature, the temperature at which the extrapolated supercooled liquid would equal that of the entropy, that of the crystal. Viewed as a paradox, because how can a liquid have the same entropy as a solid? Okay, now there's enough people in the audience who know about superfluid helium and its entropy, so I don't think this should be as alarming to all of you as it was to people back then, but I do want to point out, this is not a quantum liquid. There's no quantum liquid going on here. This is just a liquid, classical liquid. But what does it mean to have the entropy do that? So first thing is it never gets there. But in some materials, you get really close, like really, really, really close, like to where the extrapolation is not a big leap. It doesn't really matter to me, anyway, whether you could get there or cannot get there. It's what it's aiming at. And I would claim to you that what it's aiming at is actually that point there. So I want to know, back to this diagram, why have I labeled that the ideal glass? What is special about that state? Well, it is special. It's the lowest energy of any amorphous structure. The crystal can be lower, that's one of those arguments that's not worth having, because I don't think there's any proof that the crystal has to be lower in any given material. But that's not the point of this argument, so let's not have that argument. So this plot is shown with the enthalpy being higher, the internal energy being higher, but that is the ideal glass. It is the lowest energy state other than the crystalline state. Well, how many of them are there? There's one. What's the entropy of a unique state? 0. So I would claim this is not even a paradox. This is just an is. Now, it does rely on one important point. There is a single state at low energy. There are obviously lots and lots of things that have degeneracy in their energy states. But ironically, I would say, and this is ironic, it's easier for a crystal to be degenerate. You've got perfect symmetry everywhere. So people are busy making these Kagame materials, which have these massive degeneracies in their ground state that everybody hopes is going to lead to a spin liquid, et cetera, et cetera. The amorphous state is actually less likely to be degenerate. Every site is unique. So if I take, particularly if you want to mentally think of taking n atoms, it's not that surprising that there could be a unique state. So what is it that makes that state unique? It has a ton of short-range order, probably has some medium-range order, doesn't have long-range order. But what really underpins both energy and entropy in the end, if you think of them as having to do with atomic bonds? It's all local. All energy is dominated by the nearest neighbors. So I would claim it's not even that surprising. This is, in fact, a calculation of a Leonard-Jones potential. We claim it's not even that surprising that there should be a unique lowest energy state, and so we call that the ideal glass. That ideal glass has no entropy, has a low enthalpy, and so then what's the connection to what I've said before? So first thing is that's what I mean by hidden order. It doesn't look ordered, but there is a hidden order because it has to have a hidden order or it would still have entropy. All right, so final point on this is vapor deposition, unlike liquid quenching, I don't have to rely on bulk processes. Like the equilibrium, the glass transition always happens, you fall out of equilibrium. But I can grow a thin film at, let's just make up a number here, because it is a made up number, 0.8 of the glass transition temperature. At 0.8, and TG depends on kinetics and all kinds of things, but it doesn't vary that much and it doesn't matter for the argument I'm going to make. Grow at 0.8 of TG. There is no bulk mobility. So in the bulk, you will never reach equilibrium at 0.8 TG. Lifetime of the universe, you wouldn't get there. But I have all this surface mobility. So in vapor deposition growth, the atoms can move around and find the equilibrium. Now, the question is, under what circumstances? And that's the thing we're trying to investigate. But what I believe, and what we've seen now in a couple of examples, is vapor deposition allows you to find that ideal glass state. So the whole point is, what you actually want to do is you want to grow at TK. The whole magic comes in, grow the film at TK, at that temperature at which that is the equilibrium state. You better have enough surface mobility to reach an equilibrium, but the idea is to grow at TK. If you can grow at TK with a good surface mobility, then you hopefully reach that state. And the connection now to everything else is that state has, this is schematic of course, but that state has multiple levels nearby. The ideal glass state has no TLS because there are no nearby states. That's the whole point of that state. If there was another state that had similar energy, it would have to be very far away in configuration space because it would have to involve a rearrangement of like all the atoms. So it's not surprising that this, if we can reach that ideal glass state, that we would have no TLS. And I claim that's what we're seeing in our amorphous silicon. Okay, and theorists actually like this. There's something called random first-order transition theory, which basically postulates something like what I'm just saying. Okay, so that's that. Let me just, I think I only have one more slide. So I'll just show this. So this is now a super technical point, but remember I told you there was no explanation for this universal glass range. Now let me plot amorphous silicon. I'm going to plot it as a function of density, not growth temperature. It turns out the atomic density actually explains all of our data on the TLS, and it turns out there's something to do with those nanovoids. But the real point is, that's the scaling parameter. So this is what I get in inverse Q. There's the universal range in gray. There's my really low TLS, so if I, the really, 2 orders of magnitude. There is, as I make it worse, meaning lower density, there it is going up, and look what happens. It saturates in the universal range. We've had this data for like 6 years at this point. I've not yet gotten a theorist to help me explain it in a way I feel comfortable submitting it. I suspect it has to do with interactions between the TLS, something like that, but it is saturating. And what's weirder than that, what is this? Okay, what's weirder than that is if I include our heat capacity data on the same plot, that's the black curve, they keep going up. So the TLS as measured by heat capacity line up quite nicely down here at high density where there's not very many TLS. Then they saturate in this range as though they're interacting, but the heat capacity just keeps going up. So that's the part that we have had trouble explaining. I think we've got some clue here as to what's missing in the standard tunneling model, since we've got something that saturates in that range. Okay, and then so final comment I'll make is somebody asked me yesterday, this seems like what I'm saying is universal, like we should be able to do this with every material. In fact, my hypothesis is that what's universal about the universal glassy range is the universal nature of liquid quenching. Since all of those early samples were all made by liquid quenching, the transition through the glass transition in a liquid quenching process, when normalized by the temperature at which that occurs, I believe that's the universal part. We'll see. Anyway, the point is we tried to do this with silica because we desperately need a second material that does this. And what happens with silica, first thing is you'll see all of it, all of it is in the universal range. So we failed. It doesn't, it does change as I change the growth temperature. It goes down, but it goes down by a factor of 3, not a factor of 100. So it's also failed in the sense that the silica we make by vapor deposition does not do this magic thing. It is actually worse silica than you can make by liquid quenching. So my silicon gets so close to the crystalline density as to be identical. The silica, that is not true. So we are not making the language, which I haven't mentioned to you previously, but if you've seen it in the literature, it's called ultrastable. We have not made ultrastable silica. We have made ultrastable silicon. So this doesn't disprove anything. It's just, we can't make the ultrastable thing, so we aren't anywhere near the ideal glass. So silica just failed to test this. Now, what I'm not going to be able to do, I'm just going to tell you about gravitational waves, but I'm hoping you've already seen. So it turns out they care about this. Hopefully you've all seen stuff about gravitational waves before, so I'm just going to tell you why anything I told you has anything to do with gravitational waves. So there's the gravitational wave stuff. There's the schematic of what this looks like physically and the 2 arms and things like that. I hope you've all recognized what an amazing thing they're doing where they're detecting displacements of mirrors that are 10 to the minus 19 meters. And if that doesn't mean anything to you, let's just call it 1,000th of the diameter of a proton. So one arm gets longer by 1,000th of a proton, diameter of a proton, the other arm gets shorter by that same amount, and they can detect that, which is an astonishing idea, and I'm happy to tell you all about how amazing it is, but trust me, the technology here is astonishing. Okay, so they do that in part because they have 800 kilowatts of circulating power in there. There is no 800 kilowatt laser that is circulating power. It all depends on these test masses having mirrors on them. You cannot if you put a metal mirror in here with 800 kilowatts of circulating power, the skin depth of a metal is, the absorption, you would not only vaporize the mirror, you would vaporize the entire end station. That's just a huge amount of power. 800 kilowatts is an insane amount of power to have hitting anything. So they don't use metals, they use instead Bragg reflectors. And so the Bragg reflector is a high index, low index insulator. So it's all about, you have to have no absorption, and then you use a high index, low index, quarter wavelength thing to get really perfect reflectivity. So this is just a really cool picture because that is perfectly transparent if you look at it head on, but you can see the reflections, and it's an astonishing thing they're doing. So this is a thing that shows you all the sources of noise, and the point of all this is after all they've done, and it is they, but it's now we, because now I'm involved too, there's all kinds of things they had to do technologically to beat the noise down, to make it possible to do what they're doing, to where the leading source of noise at this point is this thing here, which is called thermodynamic mirror surface fluctuations, often called just thermal noise. What that is the mirror, they're big. These test masses are big. They're like 32 centimeters in diameter. They have to be amorphous because there's no crystals that you can make that big and this flat. So they're all amorphous coatings. High index is right now some tie-dope tantalum thing. Low index is silica. And the thermodynamic surface mirror fluctuations are those little things that I showed you before as tunneling level states. This is the room temperature thermally activated part of that. Little tiny motions of the atoms in the surface. And fluctuation dissipation theorem tells you that the internal friction that I talked about before is the way of measuring this. And so, where's my equation? There. Okay, so this is the equation that you get out of a fluctuation dissipation theorem. This is the spectral noise. It's dependent on temperature. It's dependent on frequency. It's dependent on, that's the radius of the laser beam. It's dependent on the Young's modulus, blah, blah, blah. That phi is the mechanical loss in the mirror, in the coating. In the coatings. And it turns out silica has, the amazing power of silicon and silica, both separately. So silica at room temperature has this enormous dip. It is an amazing material at room temperature and only at room temperature. And so that is the leading source of noise right now. And it's limited right now by the high index layer, which is the tie-doped tantalum. And so I'm the first person who was able to show that I can reproducibly, now what I really showed was the low temperature loss, but it's not orders of magnitude at room temperature, but it is factors of like 3 or even 10 at room temperature. But I can reproducibly and controllably reduce the mechanical loss in amorphous silicon. And if we could make that work on tie-doped tantalum, well, I would not be part of LIGO anymore because it'd be solved. But we can't. It's proving not to be as simple as that. But I was invited to join LIGO, the LIGO collaboration, based on our ability to tune this controllably and reproducibly in silicon. So that's where we are, and I will just end there. So we're busy trying to find a second material is kind of the idea. Silicon right now looking like it's magic. I don't believe in magic. I was asked to write a review article one time recently that was called Amorphous Silicon, the Exception That Proves the Rule of Universal Glass Properties. And I said, I'm sorry, but that's not a physics thing. There is no such thing as an exception that proves the rule. That's just silly. So we titled it and said, The Exception That Points the Way to a New Rule. So that's our idea. But so far it is unique, so that's annoying. So let me just conclude, and I'll just put these up here, and then just make sort of global points. So I hope I've convinced you that amorphous materials show many, if not most, of the properties that we seek to describe in condensed matter physics. Some of those properties are reduced, some are improved. They are not simply a mess. They have defects, they have local structure, they have controllable properties just as much as crystalline materials. Growing an amorphous film at a higher growth temperature, which is counterintuitive to most people, but that's the underlying point. You grow it at the highest temperature that you can just before it starts to crystallize. Once it starts to crystallize, it's inhomogeneous, and you should not. I went through a student's, not quite thesis, but almost thesis in a trash can because they brought me a whole bunch of work on a partially crystallized material. So it's just inhomogeneous. I don't want to look at inhomogeneous materials. Mechanical loss can be reduced to near crystal values, well below the universal range. Then all these other properties can be significantly larger than in crystalline counterparts. Strong disorder, which many people think is a bad thing, actually is an interesting thing. It makes electrons more localized, which is not necessarily bad. So things like Coulomb interactions become stronger, spin-orbit coupling is enhanced. So in some ways, localizing the electrons is a good thing. Topological states and these things have to be rethought to not rely on crystal structure, but instead rely on a local structure. That's something we're working quite a bit with, Adolfo and Peru and so forth, thinking about how do we find markers, how can we describe these properties. And finally, how to predict them, try and calculate invariance, and then the final points. Final global point. I would suggest to you that amorphous systems are a pretty wide open field. It allows us to find new phenomena and new material systems by expanding to the strong disorder limit and not being limited by crystalline stability. theories to date, and I haven't stressed this quite as much, it really goes all the way back to my beginning point about superconductivity. Theories of most condensed matter properties rely very heavily on the crystalline structure. And the question is, can we generalize? Can we learn from that? Can we think in real space instead of reciprocal space? And will we learn something about the phenomena, like the superconductivity? I think we have a deeper understanding of superconductivity from realizing that it is about time reverse states, not just plus minus k state. And so then the final comment is, well-prepared amorphous materials approach this ideal glass state. And that's what I mean by hidden order. So thank you.
So thank you very much for a lovely talk. And it's open for questions.
Thank you for a really interesting colloquium. I got the impression from you that this high surface diffusion was really important to creating this amorphous state, and that you want to find as dense a packing as possible, which is like this ideal amorphous state. But I always thought when you have high surface mobility and you're growing a film from vapor deposition, you end up with this diffusion limited aggregation where that creates a lot of voids in dendritic structures, which seem to be counter to what you were saying. Why don't you get DLA?
You do. So did people understand the question? There's a long, there's literature going way back on this diffusion limited aggregation. If you grow at low temperatures, you very much get that. In fact, I don't know if you noticed in the amorphous silicon I showed, which was grown by E-beam evaporation, you could actually see these columns in there. Now, and that's a common thing in E-beam growth. Sputtering does not do that. Sputtering, because you're doing this sort of, high energy peening, it's often called. You sort of, it's high energy, so they're literally sort of little, like a ball peen hammer, sort of. So you end up very different structural appearance. We've grown amorphous silicon by sputtering also, by the way, and then it doesn't have those columns. And one of the things I like to check is that the columns don't matter. So we regularly will try to grow amorphous materials by both E-beam, which is a low energy, doesn't sound low energy, but it is. It's a thermal evaporation, so that's milli-electron volts. Even when it's tungsten and it's, thousands of Kelvin, it's still it's not, with sputtering is like tens of electron volts. So they're very different, kinetic processes that go on. It's really valuable to show that whatever properties I'm measuring don't care about that structural difference. So the diffusion limited aggregation that you're talking about, we definitely see. In fact, if you start growing at very low temperatures, you do see much more of that dendritic process, and that is what happens when you don't have a lot of mobility. But start raising the growth temperature, even those early papers, if you start looking at the effect of raising the growth temperature, that surface diffusion wipes out the diffusion limited aggregation. But there is yet another competing process which I feel like I should mention, even though you didn't raise it. At some point you start crystallizing. So if you give it a lot of mobility, you'll actually nucleate, crystallize. And the important word there is nucleate. I didn't talk about this at all, but I referred to at one point ultra stable. There is starting to be quite a body of literature on using vapor deposition to grow what is called ultra stable glasses, which the definition of that is more stable than liquid quenched, by which you mean lower in the energy landscape than liquid quenched. Turns out it also means more resistant to annealing after. So there's a bunch of meanings, but thermodynamically you're lower in the energy state. So you can see that in things like the glass transition. If you grow at a higher temperature, you're lower in the energy landscape. Therefore, you have more energy to release when you go through the glass transition. You're going further, you've got more energy available. If you grow at low temperatures, we've actually just recently coined a new word, which is substable. You can, by vapor deposition, if you grow at low temperatures, which is starting to get close to your diffusion limited aggregation limit, if you grow at low temperatures, you're higher in the energy landscape. You get caught somewhere up here, which means you're less stable. So you have less enthalpy to release when you go through the glass transition. So there's a whole, and in all of that, it also, being higher in the energy landscape, makes it more likely to crystallize. It's like it's got a lot of energy trapped in the structure, and so it's more likely to crystallize and things like that. So the crystallization is a nucleation thing and kind of competes with all of this. So, but you're not wrong about the diffusion limited aggregation. That is, the original paper that showed that was all on the limit of atoms sticking exactly where they landed. So it's like diffusion competes with that process.
Okay, more questions?
So thank you for a very beautiful talk.
Thank you. A little long.
There are other characteristic properties at low temperatures of glasses, such as the T-squared thermal conductivity or thermal conductivity plateau, or anomalies in ultrasonic attenuation.
Yes.
So I was wondering whether those experiments have been done on your amorphous silicon samples.
So that's a great question. I talked about only two properties because they're the two that we have actually measured. We have done the thermal conductivity. Turns out we were actually I was talking to Andreas just yesterday about thermal conductivity. Turns out to be it's a trickier measurement, and people are very naive about how to interpret the thermal conductivity. I mean, almost everybody goes directly to the, what's it called, the 1/3 CVL limit, which is a kind of absurdly naive view of thermal conductivity. So in our thermal conductivity, so we have seen, and they correlate. So the thermal conductivity of our amorphous silicon the K-squared term does go down. The plateau is a different topic. I'd have to pull out that data. We do have the very first paper we wrote on amorphous silicon. We had the thermal conductivity in it and did talk about exactly that issue. And I'm trying to remember what happened to the plateau. It's a slightly different phenomenon. The boson peak is a whole nother thing, by the way. When I said, doesn't this boson peak look the same in silica? So it does in silicon too. It kind of is in the same place and so in crystalline materials, that's just a zone boundary phonon thing. I shouldn't say just, but it is it's zone boundary phonons. It's not really a very complex phenomena. And it's hard for me to see how that isn't the same thing in the amorphous, that it is not some sort of what is a zone boundary phonon in an amorphous material? Well, it's a nearest neighbor thing, so I don't know. So anyway, I should pull out that paper, and because some of this we did talk about. The ultrasonic attenuation has not been done. We have looked, dielectric losses are, yes, so that is a huge one, and obviously you're nodding because, so dielectric losses, of course, the whole world is mesmerized by qubits right now, and there's and decoherence of qubits, and decoherence of qubits is all at low temperatures and is almost certainly something to do with tunneling states. So we did work with people at Livermore on doing microwave resonator strips. And the end result was our amorphous silicon, it doesn't correlate. So the mechanical loss went down by orders of magnitude. The dielectric loss only went down by like a factor of 3. And it doesn't correlate. So the standard tunneling model is clearly incomplete, which everybody knows it's incomplete. It's quite obviously incomplete. These are, really, now I'm getting very specialized, so nobody else should worry if you don't understand a word I'm saying here. But they're in totally different regimes. So the dielectric loss is measured at gigahertz. The mechanical loss is measured at kilohertz. One of them is in a resonant regime, one of them is in a relaxation regime, which to those of you who know about the standard tunneling model, those words will mean something. For the rest of you, they're different. So maybe we shouldn't be surprised that but they not only don't correlate, they cross each other. So we have mentioned briefly that thickness matters for our amorphous silicon. So we can do this interesting thing of reaching the same value of atomic density by either growing at high temperatures and low temperatures and thick and high temperatures and thin. So we can crisscross growth temperature and thickness to get to the same density. And that will result in the same mechanical loss, because everything's scaled with density there, but really different dielectric loss. So I think the really bottom line on what I'm saying right now is we found that dielectric loss actually correlated with dangling bond density. And dangling bond density does not correlate with any of the things I've talked about, so I didn't really mention them. And maybe one shouldn't even be surprised at that. Like, where does it, you have to have a dipole moment to have a dielectric loss. So where is the dipole moment in a monoatomic material like silicon? Like, why does it have a dipole moment at all? So maybe a dangling bond makes sense. So experimentally, it correlated with dangling bond density, which the mechanical loss does not. Mechanical loss just literally crisscross. Like it goes, it just doesn't work to try and dangling bond densities. So I'll add one more piece, which I haven't talked about at all here, but people might find it interesting. Anybody who knows anything about amorphous silicon knows that it has been decades since anybody grew, except for us, grew amorphous silicon without hydrogen. Because for electronic properties, you have to get rid of these dangling bonds. By the way, there's not very many dangling bonds. I mean, dangling bonds are terrible for electronic properties, but there's like a part in 10 to the 4, 10 to the 5. It's like a really lot of dangling bond density would be 10, well, we grow some films with 10 to the 19 dangling bonds per cubic centimeter, which is a really large number and totally unacceptable for electronic properties. But that's out of 5 times 10 to the 22 atoms per cubic centimeter. So, like, if you looked at this material and tried to find the atom that was missing a neighbor, it's like 1 part in 10 to the 4. And that's particularly bad, that 10 to the 19. Mostly we're 10 to the 18. So, and by the way, to add a further weirdness in this from a technology standpoint, the way you get rid of these dangling bonds is you put hydrogen in. Okay, that sounds fine. Hydrogen's a proton. It can go around, find that dangling bond. But if so really classic amorphous silicon, it's like anywhere from 1% sometimes is enough, but usually it's more like 10%. So why in the world do I need 10% hydrogen to get rid of a part in 10 to the 4 of dangling bonds? Like, what are all the other hydrogens even doing in there? And there is no answer, and nobody worries about it. So in technology, they just do it. In fact, different techniques take different amounts of hydrogen. So we've recently started playing with adding hydrogen, and it turns out, so we can get rid of our dangling bonds like everybody else can with added hydrogen. So it turns out that hydrogen does way more than getting rid of dangling bonds. It also facilitates structural relaxation. So in addition to getting rid of dangling bonds, it improves the density of the films, it reduces the mechanical loss of the films, and it looks like it might, it reduces the optical absorption, which if you're LIGO, that's what you really care about, is optical absorption. I'd love to get some theorists interested in this problem, but anyway. So we are currently working with Sunil, I'm not going to get his last name right, at Caltech, who's doing superconducting strips because nobody has yet tried. We're hopeful that this hydrogen might also help with his losses. So we don't know. That was a long-winded answer with a whole bunch of pieces to it.
Okay, last question maybe?
Yeah, I'm puzzled by this material that you say might become topological with amorphism. So I'm wondering if there is so typically non-trivial topology in band structure, we understand it as when longer range hopping parameters become dominant, which facilitate the twist over the Brillouin zone. So I'm wondering if you have a microscopic understanding that from the crystalline phase to the amorphous, you tend to have longer range hopping parameters. Can you say something?
Okay, so pretty soon I'm going to actually ask Adolfo to answer this question. She says giving Adolfo a little bit of heads up notice. But what I will, so the part I would like to, okay, did you actually get your answer? Because
you can invert two orbitals locally by spinning coupling.
Right, there you go. So I was going to say there is a way in which, as an experimentalist, I like to think of this, which is that if I try and think of what, even think about Berry phase curvature and things like this. So on each site, I can talk about spin momentum coupling. And either spin parallel to momentum is preferred or spin anti-parallel. And then I can hop from site to site to site around some little tiny local loop, and there will be an energy difference whether I hop around with everything being parallel or everything being anti-parallel. So it was early on, actually, when I was first talking about the Berry phase curvature stuff, the intrinsic anomalous Hall effect. The first thing that actually Michael Flatte, I told him about my data, and he said, "Oh, you just have to calculate the spin-orbit momentum coupling structure, band structure, or something like that." And we've never done that. I've never actually gotten a theorist to help me do that calculation. So what we instead do is the thing I described. We take this giant unit cell, and in this giant unit cell with hundreds of atoms, we literally melt it in the computer, we quench it, we then anneal it gently, and this is really a royal way, although because mostly this is working with somebody. We then anneal it gently, try and let it find its local minima, stuff like that, and then we do a traditional Berry curvature of this giant amorphous thing, and then we repeat that like 20 times. And you can also do checks like check that it doesn't change, that your result doesn't change when you double the cell size and stuff like that. So it's kind of a cheat in the sense you're still doing a crystal, but it's a crystal that is hundreds of atoms in size.
You may learn quite a bit by projecting on linear basis and look at if there is some qualitative.
That may be, that paper I referred to, that FISREV letter, the Chenoy et al. FISREV letter, that is, I think, what they did. And again, I may have to refer you to the two, not only Adolfo but Peru sitting in front of you, because they're going to be better at answering that question than I am. But thank you. Yeah.
I guess we are over the time, but I think as a theorist, I'm fascinated. You kind of invoking the hidden order,
right?
Which is a very important concept, right? And you're not telling us what it is.
Okay, so let me start with the simple and what I'm saying is if it has no entropy, there has to be a hidden order. So the fact that we can't see the order doesn't mean it isn't there. So I mean that is literally.
What is it? Do you know?
Okay. So you're asking a deeper question, which is a great question. Often people ask me how do you. I guess it was best put as how do you define amorphous, and to which I used to just very happily give this following answer, and the answer is. It's not crystalline, it's not even nanocrystalline, and it's not quasicrystalline. The problem with that answer is sort of obvious because I've already kind of previewed it. I'm defining amorphous by what it's not. And that always seemed to me perfectly fine. I was defining it by what it's not. It's not any of those things. It's something else. And then there was, wasn't that long ago, in fact, the past year I was giving this talk somewhere and somebody actually basically raised the same question, like, how do you, it's like, that's fine, I'm defining it by what it's not, but what is it? And all I can say is it's got short range order and medium range order and no long range order. So I still come back to it's got short, so I think one can define it in terms of, you get in trouble when you start doing structure, though. Everything's big, broad distribution. So I don't think I have a better answer than by saying I know what it's not. It's not all. So it has short range order and medium range order and no long range order. But it's not nanocrystalline.
I think you went pretty far already in the logic of pointing out the existence of it. I thought maybe you had some ideas.
I don't, but I'm seeing a hand going up back there because maybe somebody actually has a suggestion.
I had a related question.
Okay.
So we can look at spin-out materials,
yes.
Where you have, it's a crystal, but within the crystal, so they lack long-range order, but they do have long-range correlations in the form that you have two spins pointing in and two pointing out at each vertex. And that has a signature in the neutron scattering pattern, in that because there's long-range correlations, you get sharp features in neutron scattering. I was wondering, because you don't have long-range order, as you said, but you do have 4 coordination on every site, which sounds very similar. So I was wondering if there might actually be a signature of that, say, an X-ray diffraction. I guess, do you just see a ring in X-ray diffraction?
You see a ring. You see, actually,
it's maybe like sharper than it would be if you didn't have the coordination the same on every site or something like that.
Yeah, that's probably true. So
then that might actually be an indicator.
I'm trying to see if I actually show the diffraction pattern of silicon here. I mean, I can pull it up from something else.
And then maybe a comparison to something that doesn't have
yeah.
this local.
Oh, no, I don't. So I do have, but so the short answer to what you're asking is there is a sharp ring with no spots. So that's what we look for so we look for 2 things to prove we have something amorphous and not nanocrystalline.
Right.
That you cannot distinguish an X-ray diffraction. X-ray diffraction has broadened peaks. Once you get down to about a few nanometers of a nanocrystal, it looks exactly the same as the amorphous. You just can't tell the difference. So it's one of the problems in my field is the literature is full of things that people call amorphous based on X-ray diffraction, and we know for a fact that X-ray diffraction won't distinguish. So what we look for in the is we take high resolution TEM, which shows in particular no lattice fringes. So lattice fringes show up pretty early, and it shows what you're asking. You see a relatively sharp ring, but no spots. And so, yeah, I guess I haven't.
I think the sharpness of the ring maybe could be used.
Yeah, I mean that's an interesting question. I don't know that we've ever. I mean, you could ask the same thing about liquids. In fact, it probably is the same problem in liquids. I mean, liquids also don't have long-range order, and also are not nanocrystalline or quasi-crystalline or. Yes, you may be going to say something here useful.
I find it really surprising that it has. So I'm trying to get to this hidden order you're pointing to. So it has no long-range order. So that, but it has extremely low entropy. You
right.
would likely even say 0 entropy.
Yeah, the ideal glass. Whether we can get there or not is a separate question than that it theoretically exists.
Because if it's not a crystal, then there must be many equivalent positions.
I don't agree. So let me go.
Because if it's not a crystal, then there are many. Just by you deviate every position by epsilon, and you can create many equivalent positions. And you can, if it's a quantum system, now you could make.
Yeah, no, not this. So, but I'm just going to point back to this figure. There are calculations that show unique ground states.
But calculations can never prove it, right? Because in a computer you get stuck. Just like
No. This is not. This is calculations of a Leonard-Jones potential. I mean, so they just let it. They put random atoms in there. So I'm going to politely disagree because I think the intuition is that there's always going to be a degeneracy in the ground state, and I don't think that is true. And I will just, I mean, in part, this is a canonical figure that I'm showing. Calculated lots of degeneracy, but there really is still a minimum in there. And so, I mean, I think there is an underlying question. How do I know which materials would have a unique minimum? Amorphous silica, for example, I mean, again, you get into specific materials. So amorphous silica, unlike amorphous silicon, has a kind of special structure. So amorphous silica, each silicon has 2 oxygens, and that angle is, that's 3 atoms. Okay, let's just do that. So 2 atoms. So 1 oxygen and 1 silicon and 2 oxygens. So that angle is very well defined in all silica. But the angle to the next one, let's do that. Maybe that's better. Okay, there. So now at least I have 2 equivalent bonds. So oxygen, oxygen, silicon. This has got to be the same oxygen. So we're just going to go like that. So 1 oxygen bridging atom. So that bond is extremely floppy. And that is the reason that crystalline silicon has about a zillion, what's the word that I want? The allotropes. Do I mean allotropes? I think I mean allotropes. All the different crystal structures. So crystalline silica has like 10 different structures it can form, which are all about that flop. So this angle never varies, but that angle can vary all over the place. So obviously, I think obviously, in the amorphous structure, that is going to have much more degeneracy because I can make that angle, vary a lot. And that's one of, so in terms of my arguments, the Kautzmann temperature, in fact, this is known, the Kautzmann temperature for silica is very low. And you actually get the Kautzmann temperature from looking at the heat capacity of the liquid state. So it's not at all to do with a solid. It's you get Kautzmann temperature out of the heat capacity of the supercooled liquid. And silica ends up having almost all of its entropy is already gone, or all its, not, actually I mean enthalpy here, is almost all gone by the time it hits the glass transition. So the glass transition in silica has a tiny signature in the heat capacity, really tiny. And so if you look at the heat capacity, the way you get the Kautzmann temperature, I mean here it's an extrapolation, but you can plot this in enthalpy space instead, which is another way of looking at it. There's only a tiny bit of energy lost at the, even at the crystallization. So the heat capacity is not that much higher in the liquid state than the crystalline state. So the extrapolation is like, takes TK down to 2 Kelvin or something like that. So my underlying hope is that this is all about TK. And so how do you get TK? And again, that's a liquid phase property, actually, not anything to do with glass freezing. It's about the difference in heat capacity in the liquid compared to the crystal, both of which can get measured. So you want, if the Kautzmann temperature is super low, there's 2 problems with that. You're not going to have any, I'm not going to be able to grow it at that temperature, and even if I did, there's no mobility. So in the end, I'm going to end up arguing that I want a fragile glass so that I get the Kautzmann temperature up high enough to be useful to me. At least that's the idea we're exploring. And whether a fragile glass inherently has fewer, has a more well-defined minimum, I think we do need theoretical guidance on this. Like, when is the minimum unique and when is it not unique? I don't think it's intrinsic to the amorphous state that it has to have a I don't think that's intrinsic, that it has to have a degeneracy. But that's that is a speculation, let's say.
Okay, I think we have to close the session, and thank you so much.